Welcome to Calc Chats 21. Today we're going to be talking about the fundamental theorem of calculus part 2. This is also known as the Anti-Derivative Theorem. We're introducing this new idea today called an accumulator function, and basically it picks up the area between the bounds. So if I'm looking kind of at just this function right here, and my bounds are, let's say, from a to b, any x I choose in this interval, that area underneath the curve can be represented by this function right here. And so we just kind of say it picks up that area between a and x, where x is between a and b. So now the fundamental theorem part 2 says, if our function f is continuous on this interval, and we have this accumulator function, then this function also has a derivative at every point on x between a, b, and then derivative is defined as the derivative of the integral is our original function. And so this makes sense in a way. When we take the derivative of the integral, we should get back the original function. We're going to see what that looks like in terms of examples. So our first example is the integral from negative pi to x of cosine t dt. And this is just asking me to find the derivative of the following. And so I know that I need to take the derivative with respect to x. But the problem is I'm in terms of cosine. So when I take the derivative with respect to x, I want to plug x back in. But remember, kind of with our chain rule, we need to take the derivative of whatever is plugged on the inside. And so this ends up being cosine of x times the derivative of x is 1. Ooh, I'm going to write this to the side. The derivative of x is just 1. And so this ends up just being cosine of x. And so where we need to plug in x wherever we see t, then we need to multiply by the derivative of whatever our upper bound is. And so this lower bound, it could be anything because we end up taking the derivative. It doesn't matter because we could start anywhere, and when we take the derivative, we're just focused on that x. So this one looks pretty similar. Again, I want to find the derivative with respect to x. So I'm going to take my function, plug in x squared, that top bound, wherever I see x, and then I need to multiply by the derivative of x squared, which is 2x. So I should end up with 2x cosine x squared. So my smartboard hates me and just decided to stop working. So that was an awkward moment of silence, but there we go. 2x times cosine of x squared. This one looks similar. So we're still trying to find the derivative with respect to x. So this one looks similar, but my bounds are messed up. So if we remember our integral properties, if we take the integral from 1 to 3, that's the same as the negative integral from 3 to 1. So when we switch the bounds, we add a negative sign. So all we need to do is add a negative sign to take this from 5 to x, 3t sine t dt, and now I can use the fundamental theorem of calculus. So now I want to plug in wherever I see t, I want to plug in x, and then times the derivative of x, which is just 1. So I just end up with negative 3 sine t. Here's a DIY problem for you to try at home. This one is a little bit more difficult, so I'm going to kind of start you off. So both of our bounds have x's in them, and we can't have that. So what I'm going to suggest that you do is I'm going to suggest that you split it up into 2 different bounds. So if we remember, again, our integral properties, we said the integral from 0 to 2 plus the integral from 2 to 4 was the whole integral from 0 to 4. And so the way I'm going to split this up is I'm going to say, okay, the integral from 2 to x to x squared is equal to the integral from 0 to x squared minus the integral 0 to 2x. So this is kind of like our whole integral, and in order to find from 4 to 2, I need to subtract 0 to 2. So again, this is just basic integral properties that we covered last quarter. We're just using them in a different scenario. So let's take this integral from 0 to x squared of 1 over 2 plus e to the t dt minus 0 to 2x, 1 over 2 plus e to the t dt. So take a minute to copy that down and try this yourself. And so what you should end up with is x squared over 2 plus e to the x squared minus 2 over 2 plus e to the 2x. Using the fundamental theorem of calculus, we can create new functions. So I'm asked to create a function with the following conditions: that the derivative is equal to tangent, and that f of 3 equals 5. And so I can use this idea that the derivative of my integral is my original function. So I can say y equals the function from 3 to x tan t dt, because remember, if I take that integral, or if I take that derivative, I end up with just tan of x. So this meets the derivative condition, and it's asking me that f of 3 is equal to 5. And so when I originally plug in 3 to this integral, if we use our integral properties again, remember the integral, that's not what I want. The integral from 1 to 1 is 0. I'm not picking up any zeros. So when I plug in 3 for x up here, I should get that this function is 0. So all I need to do is add 5 to the end outside my integral in order for this to be true. Because again, if I plug in 3, the tangent t dt, the integral, that all turns to 0 plus 5. So that meets the condition that f of 3 is equal to 5. So this is it for Calc Chats 21. Again, we're just using those properties and derivatives and all of that stuff in order to kind of solve more integrals and more anti-derivatives. So come to class with any questions that you may have, and please make sure to like and subscribe.